All right, I'm going to demo how to do experiment 1 here, and if you want to get credit for the lab, you just have to make sure that you change your data values for your experiment. There's lots of choices, so don't use the values you see in this video. Make sure you use a different selection. So let's preview real quick what this is all about. I'm going to clear my choices here. So when you are doing this lab, you're going to study, you can change the radius, the angular speed, so that's the speed at which it's rotating, or the mass. For part 1, it says design an experiment to find the relationship between the radial force, that's the force pulling the mass in, which is the tension force, and the angular velocity. So we're going to vary the angular velocity. So we want to select angular velocity, and you notice some other choices get grayed out under the independent column and under the radius column and under the mass column. So now we have to choose for radius. We can go with B, D, or E. Once we choose one, we want to lock it in, and that's it. I'm going to go with E, which means if you guys do this, you have to choose B or D. For mass, I could go really light. I could go 50 grams, or I could go 100 grams. Notice that some of the choices disappear in the angular speed column. If I go really light, I get, looks like 7 choices. If I go 50 grams, I get about 5 choices. If I go 100 grams, I get about 5 choices. I'm gonna go 50 grams. So whatever you do, don't choose this combination of a radius E with 50 grams. Do some other combination. Now I'm going to collect 5 data points here. First, I'm going to do it for angular speed 2, whatever that is, angular speed 3, 4, 5, and 6. So I have to discover what those angular speeds are by recording some data. Okay, let's just talk about angular speed very briefly before we record the data. So anytime something moves in a circle, right, that's its path, the amount of time it takes to travel around once is t. That's called the period, right? And then the relationship between the angular speed and the period is 2 pi over t. So if we look at our units, right, for units 2 pi, the units, when we write 2 pi, we're indicating the number of radians in a circle, right? A radian is just a radius, right? It's like how many of those, if that was a piece of string, how many of those would it take to go all the way around? And the answer is 1, 2, 3, 4, 5, 6, and there's a little bit more. So it's about 6.28 of those radians to travel all the way around the circle, and that exact number is 2 pi. Okay, so you can type 2 pi into your calculator. So if we actually follow the units, 2 pi radians, and the units for the time period would be seconds, right? Then your units for angular speed is radians per second. So in other words, how many radians do you cover in 1 second, right? So to collect that data, right, we're going to have to figure out how long it takes to travel around once. That'll be our t value. And once we get our t value, we can just do 2 pi divided by t to solve for the angular speed in radians per second. Okay. Now, the radial force will be easy to collect because we've got this cylinder spinning around, and the force here, the force is on the cylinder. We've got the force of the Earth, which is the gravitational force. We have an equal and opposite normal force of the table, and then we have, I'm going to label FR for the radial force, pulling it in. If you were asked to model the net force on the object, you would eliminate the gravitational force and the normal force because one's positive, one's negative. They're acting opposing to each other, but they're equal in magnitude, and you'd be left with this radial force, which is the only thing in contact with the object is that string that's connected to the tension apparatus, I'm sorry, the force apparatus, the force scale through the pulley. So we're going to record how the force changes, the radial force changes as we change the angular speed. And then we'll figure out what this graph looks like. So let's go ahead and do it right now. Let's collect some values. Don't forget, this right here is called our independent variable, and we modify that. That's our input, and then the output is the dependent variable that varies as we change the independent variable. So let's go back, collect some data. So here we go. I'm on an angular speed of 2, mass 50, radius E. I hit load, and I grab my tools. I'm going to make sure that I start it when the cylinder is facing me, or try to anyway. So I'm going to back it up. Whoa. All right. Sorry about that. This is tricky. Okay, here we go. We're going to reset my clock to 0 and see how long it takes to get right back to where it is. Okay, so I'm going to try to, well, that's pretty close. For the sake of the video, I won't spend too much time trying to get it perfect. 2.9167 seconds. All right, so let's go to our data table. So this is called capital T. This is the period, right? The units are seconds. The variable is T. I guess we could write period. All right. Now we can use the period to find the angular speed, right? We had a formula for that. So we could say angular velocity. The units are radians per second. And the variable is a W, a lowercase w. All right. So we recorded 2.9167 seconds, I believe it was. Now, we're going to put a formula in for angular velocity. So we click the 3 dots, and we can say, there should be a formula option. Oh yeah, sorry, change column formula. Whoa. And we're going to take the period value. Actually, we're going to write 2 times pi. Right? We don't have pi. Let's just use 3.14159, and then we'll divide by the period. All right, so 2 pi divided by the period. That's not the exact value for pi, but 6 significant digits is enough. And then it'll automatically calculate our angular velocity. So the bottom line is it's saying it's traveling about 2 radians every second. Well, and there's about 6 radians in a circle. So it should take 6 seconds to go around if it's covering 2 radians every second. Sorry, 3 seconds to go around. And that's right, 2.9 is about 3 seconds. Okay. So that makes sense. You know, just to really clarify, I think it's important to understand that. So what it's saying, if our angular velocity is 2 seconds, it travels this far. That's about it's 2 radians. Sorry, I'm all over the place. 2.1 radians per second. So this is about 2 radians, and that takes about a second. Then it goes another 2 radians, and that takes a second. Then it goes another 2 radians, and that takes a second. It's actually, it was 2.1, so it's a little bit more than 2. So it gets us past where we started. So it takes about 3 seconds to do the whole trip. And that's what we saw. It was 2.9167. Good. So now we got to measure the force. So insert a column to the right. And we'll say radial force, because those measured in newtons. And the variable, we'll say F sub r. Okay. Now let's go back to our drawing. It looks like if each mark is 1/10 of 0.2, each mark will be 0.02. So 0.02, 0.04, 0.06, 0.08, 0.09. I'm getting a reading of 0.09 newtons, right? It's almost at 0.1. So almost at 1/10. So I'm going to say 9/100ths. Whoops. So my force was 0.9 newtons. I'm sorry, 0.09. All right, now we're just going to collect more data. So I'm going to change to a different speed. Let's load it up. I'm at 40 to begin with, so I'm just going to press play from here. Let's get my stopwatch out, set it 0.
What's that flash?
Okay, now in this case, it didn't make it all the way around, so I'm going to have to do some thinking here. I'm going to have to record how much time it took to go halfway around. So again, I won't try to be exact for the sake of time. So it took about 2.1 seconds to go halfway around, so that would be 4.2 seconds to go all the way around. So in this second trial, my period was 4.2, which means it was going slower, right? So 1.4 radians per second is going slower than before, and the force value was right on the second line, so 0.02, 0.04. Let's go to say 0.04 newtons. Okay. Let's go to the third trial. And it's not quite at the end. All right, that looks good. Reset my clock. That was pretty fast. Whoa. That looks good. So 1 second exactly to go all the way around. 1 second. And my force was about, I'd say, 0. It's almost at 0.8. So if I'm going to estimate, I'm going to start from 0.7, then I'll say 0.72, 0.74. The last line before the 0.8 would be 0.78. So I think I'm at 0.795 maybe. So let's my time period was 1 exactly. So it's going really fast. Wow, that was pretty cool. They made it match exactly. And my force was, I estimated 0.795 newtons. Okay, so notice the force went way up that time. All right, last one. Nope, second to last one. Okay, clock looks good. Press play. That was really fast. Wow. Exactly 0.5 seconds. These guys are masters of control. How'd they do that? So it took 0.5 seconds to go around. So it's going really fast now. and the force looks like it's around, so each line, the middle would be 3.5 in this case, so that's 3.1. I would say 3.13. So I'm going to estimate 3.13.